Hello, this is Elliot, and welcome to this video where I'm going to demonstrate the new forcing features in MOMDYN. So what I'm going to show you today is creation of a Duffing oscillator. So a Duffing oscillator is a pretty famous dynamics problem that will create a 1/2 frequency oscillation using a fairly simple system definition to create some very complicated dynamics. So, on that note, we're going to call this model Duffy Doherty, after the late great Michigan State head football coach. And the description is this is going to be an example Duffing oscillator. Duffing oscillator. Fat fingers here. The only other settings that we're going to change is we're going to make the time duration 10 seconds so that we can actually see something happening. And then I'm going to make this tolerance a little bit smaller so that we get a little bit of a cleaner simulation, if you will. All right, so here's my blank slate. First thing I'm going to do is go into the joints menu and create a prismatic joint. So reference points and frames are as they need to be, and what we're just going to do is create a degree of freedom. The motion is going to be in the Y or vertical direction. I'm going to give it an initial value of 2. And last, so first of all, we're going to build this Duffing oscillator using a form of a base motion where we aren't actually going to specify the motion, but rather we're going to apply a force to a large mass. And then the other thing that I'm going to do to expedite this motion is I'm going to drive it at its natural frequency. So for this model, we're going to do multiples of 10 for all our frequencies. So I want the primary frequency to be about 10 radians per second. So why setting the stiffness to 8,000 is because I'm going to end up with a mass of 80 kilograms. So with the natural frequency being square root of k over m, I'm going to create a mass that has 80 kilograms, which we'll see that in a second. So there's our joint. We've got spring behavior there and a vector measured 2 units or 2 meters away from the origin to the point A. I'm going to put a body there using our rigid body box dialog. I'll call this the base. Put it at the reference point A. Give it a density of 10,000. So a little denser than steel is one way to think of that. And then I'm going to make each side of this box be 0.2 units. Think of that as 0.2 meters. So it's like a 20 centimeter cube. And as I mentioned before, that's going to weigh exactly 80 kilograms. So looking at our model there, we can now see the nice little box drawn at the point A. And so now getting into the new features. So this is just added in version 0.8 of MOMDYN. We now have in our menu here external force, actuated force, external moment, and actuated moment. So the external loads, force or moment, are a load that will be applied at a single point or frame. We want our force to be applied at the point A. We're going to have it in the Y direction, so we'll put a value of 1 there. And then just as an example here, I'll do an example force of 100. Think of that as like 100 newtons. That'll be instantaneously applied at the start, kind of like a square wave response. And if we simulate that, you can kind of see a little bit of a wiggle there, nothing too much. But if we do look at the state plots, we can see the nice harmonic oscillation there in the generalized speed coordinate. So that tells us it's working. Of course, with the force, just doing a constant force isn't necessarily the most interesting, nor is it what we care about for the Duffing oscillator example. So now what I'm going to do with that force I just created, I'm actually going to give it a periodic input. So now we'll do 10 times sine, 10 times t. So t being the symbol for time that's built in as a default. So we're going to periodically drive this. Now, if we go in and simulate, Still not a particularly large oscillation. I'll get to that in a moment. But if we look at the plot of the states, you can see we get pretty much a steady state response at the driving frequency, getting all the way up to about 0.1 meters per second when it gets to its steady state. All right, so now the fun part. Fun for me, at least. What we're going to do is put sort of a inverted pendulum on the top of this block. So to do that, we're going to create a new revolute joint at the reference point A, and we're going to make a degree of freedom concerning rotation about the z-axis. We give the initial value of 0, initial rate 0.1, and we'll make it 1 so we can actually see something here. Now I mentioned before multiples of 10 for the natural frequencies. This one, is, of course, is going to be the pendulum that oscillates at half the frequency of the driving block. So I'm going to set a stiffness value of 25 and later put a mass on top of there that has a value of 1 for 1 kilogram. Give it a little bit of damping. Equilibrium of 0 is just fine. So now we can see the purple frame created on the block right there. Next thing I'll do is create a prismatic joint from the reference frame E, and then measuring in the reference frame C, where C is the frame we just created. I'm going to make this constant in the Y, vertical direction, give it a value of 1, so it's going to be 1 meter away. Everything else I'll leave as defaults because this isn't a degree of freedom, it's constant. Check that. We can see now there's that vector in point D coming off of the top of our block. And I'm going to create a mass, name M, value 1, description, mass. Actually, we'll say mass of the pendulum bob. That created a symbolic constant, which now we can go and create a particle. Name it Bob, our friend Bob. Put that on the point D and give it the mass we just created, which is this symbol M. All right, so let's hit play and see what this does. So we can see that little oscillation of the bob, but over time it kind of decays back to 0. A little bit of motion from the base excitation at 10 times sine t. But if we look at the states, we can see nothing terribly interesting. The bob oscillates at its own frequency, which we strategically set to be half of the driving frequency of the base, but it tends towards 0 over time. Nothing too interesting there. And then the sinusoidal input is pretty much just a constant after about 3 or 4 seconds. So what if we turn up the amplitude? So previously we created the force B and gave it this value 10 times sine 10t. Let's make it 50 times sine 10 times t. What does that do? So naturally, you're going to imagine the motion of the block itself should be about 5 times as high of an amplitude, so we'll see it a bit more. But what's the pendulum going to do here? Looks like the pendulum itself mostly decayed back to 0. Sorry for the Twitter notification there. Kind of a similar response, just everything a little bit bigger. So again, not too much to see there, but as we continue ramping up this amplitude of the external force, things should start to get interesting. Not quite that large yet, so we'll do 100 times sine 10 times t. If I had a real keyboard, I could probably work this faster. So the simulation is getting slower, which usually tends to tell us something interesting is going on here. So we can see a bit more motion of the base, and you can kind of see the bob. I mean, it decayed a little bit down from its starting point, but it seems to be less damped. And as we can see, if we look at the state plots, you can tell after the first couple cycles, actually, rather than decaying back down to 0, you get this kind of steady state oscillation. And once again, you get one oscillation in the red curve there for every 2 oscillations of the driving frequency. So now we're starting to see the characteristics of the Duffing oscillator. Again, it's the half frequency vibration, very nonlinear. You can kind of trace the fact that that red curve, it's not a pure sine wave. You can see some high order harmonics on top of it. So now let's get a little crazier still. So let's go into our external force, do 200. So doubling sine 10 times t. And I think when we run this, you should really start to see the nonlinear harmonic response. All right, simulation complete. Getting about double the amplitude of the base motion, and now you can see the unstable motion of the pendulum itself. It really didn't reach a steady state even. We can see during the 10-second period of this simulation, it just kept growing and growing. This is all very interesting to me. I think you guys can probably tell where this is going here. We're just going to keep ramping up that motion, and eventually we'll get a much more chaotic response. So at 500 sine 10t, okay. Simulate this. This one I think is going to be all over the place. So we can see it fairly quickly went into the unstable response. And looking at the waveform here, we can see almost like a triangle wave type waveform. A lot of very high order nonlinearity going on here. So point being, I'll stop the video here. For anyone who's interested, you can go ahead and play along yourself. But this is mostly a demonstration of the new forcing features in the latest version. Should open up a lot of possibilities for different types of systems that you'll be able to model. Appreciate you watching, and if you haven't yet, please go to MOMDYN.com or mobilemultivalue-dynamics.com. Send me an email and I can add you to the beta test. I'd like to get as many of you as possible using the app. So thank you very much for watching, and have a great rest of your week.